In this video, we're going to learn about logic gates. Whether you have no idea what even a logic gate is, or maybe you have a little bit of an idea, this video is perfect for you for all levels of understanding. So, first begs the question, what is a logic gate? Well, a logic gate is something that is normally found in a computer, and what it will do is it will take one or more bits of input and give one bit of output. Now, your first question might be, well, what's a bit? Well, let's define it. So, a bit is one of two possible states, and this can be anything from the outcome of flipping a coin, right? Because you could either have heads or tails. And in a computer, we represent these bits as having the two possible states of 1 and 0. Now, the first thing that might come to your head when you hear that is binary code. Because you've probably seen binary code, whether it was in a movie, in a game, or you've just generally heard that there's binary code with ones and zeros. And we'll get into what that is later. But for now, what you need to know is that a bit is one of two states, and in computers, we will use ones and zeros. So now, what's a logic gate? Well, like I said, it's something that's going to take one or more bits of input and it's going to give off another bit of output. So let's look at this. So let's say that we have a mystery logic gate here, and we are getting two inputs into this and one output. And essentially what it's going to do is take two kinds of inputs. It could be a 0 and a 1, a 1 and 0, 1 and the 1, etc. It could be any combination of these two states that we stated over here. Well, what we're going to look at here is what the output then becomes. Like, let's say here that the output is a 1. Then we could take this combination of bits and call it a logic gate. But let's look at a real kind of one. The most simple kind of logic gate is the one called the NOT gate, and in a schematic, we would represent it by something that looks like this, a triangle with a dot on it, with one input and one output. So what it's going to do is it's going to take our input and simply invert it. So if we had, for example, a 1 is the input, our output would be a 0. When working with logic gates, we like to use these things called truth tables. And what a truth table will do is tell us every possible combination of inputs and the corresponding outputs. So let's draw one for that gate that we just made. Now, it's going to be pretty simple. All we're going to do here is put in our gate the input that we want, figure out what the output is, and then write it on the corresponding side of the graph. So let's draw back our NOT gate that we just made. Again, it's a triangle with a dot, one input and one output. So, like I said before, if we were to input a 1, our output would be a 0. And while we're at it, we may as well go ahead and label this as I for input and O for output. So, like I said, when we take a 1 as our input, we get a 0 as our output. Now, this could go the other way too. We could have a 0 as our input and a 1 as our output. So we're going to graph it just like this. And truth tables are very important when working with logic gates, as they're the basis of how we understand them and how we can interpret them, right? So let's look at another kind of logic gate. The next one that we're going to look at is called the AND gate, and it's exactly what it sounds like, but let's figure it out step by step. An AND gate looks like this. It's a sort of, I would say, flat cylindrical shape, right? You have your flat line and then an arc on top of that. And the difference between this and our NOT gate here is we are going to have two inputs actually. And that means that when we draw our truth table here in a second, we are going to need more columns. So we're going to draw up something that almost kind of looks like a tic-tac-toe board. This is going to be our truth table for this. So See if you can guess what an AND gate does. We're going to label this 1 for input 1, 2 for input 2. So, you might expect for an AND gate, and you would probably be correct, that when both of our inputs are on, when input 1 and input 2 are on, then our output would be 1, is how it works. And when we have 1 saying that this input is on, and a 0 showing that our output 2 is off, then we would get a 0, because both of our inputs are not on. Not both of our inputs are on, so we would get a 0. And that goes for every other combination of inputs that is not 1 and 1. So, you might be getting the hang of it by now. And that's good, because once you understand logic gates, you can understand almost anything in computing. And once again, very important, these are called truth tables. So let's look at our next type of logic gate. The next logic gate that we're going to look at is called the OR gate. And when we draw that, it's going to look something like this. Got a curved bottom and then an arc on top of that. And similar to our AND gate, we're going to have 2 inputs and 1 output. Excuse my poor drawing. So, with an OR gate, it also is pretty self-explanatory. It turns on when either one input or the other output is on. So, see if you can figure out what's going to go into our truth table here. If you said that we would have, hold on one second. If you said that we were going to have a truth table where this side is 1 when any of our inputs are on, then you're correct. First, let's just write 1, 2, and oh. Okay, so as I stated, let's say we have 1 and 1 as our inputs. What's the output going to be? 1, because one of the outputs, at least one of the inputs is on. So that means that 1 and 0 would also end up being 1, because at least one of the inputs is turned on. The same goes for 0 and 1, saying that our first input is off and our second input is on. Our output is going to be on. And the only time that we're going to see an off OR gate is when none of the inputs are with just a 0, 0, 0. So, you're getting the hang of it. We're almost done with the basic logic gates. The next one that we're going to learn is pretty similar to our OR gate here, and that's going to be called an XOR gate. So, what an XOR gate is it is called the exclusive OR gate. And the way that we're going to notate that is by drawing an arc, another arc, and then just an OR gate right there. And we are going to have 2 inputs, just like the other few we did, and 1 output. So let's graph this. So the basis behind an exclusive OR gate is that it will only be on when only one of the inputs is on. So unlike our OR gate, it's not going to be turned on when both of our inputs are on, right? So let's graph this. So let's say that we had a 1 and a 0. Can you figure out what the output would be? If you said a 1, then you're correct, because at least exactly one of the inputs was on. So let's draw that on our chart down here. Then let's say we had 1 and 1, meaning both of our inputs are on. What's our output? If you said 0, clever, because this is an exclusive OR gate, meaning that it only turns on when exactly one of our inputs is on. So if we had 0 and 1, similar to this column, we would have a 1, and for 0 and 0, the output is just going to be 0. We have one more gate that we need to talk about, and that is called the NAND gate. And the way that we draw the NAND gate is very important. We're going to draw it just like our AND gate over here, except for one big difference. Similar to our NOT gate up here, we're going to draw a circle on the end of it. And what this circle represents is that it is NOTing the input, or the output, because this is the same as drawing something like this, where we have an AND gate going into our NOT gate. So, given this information, see if you can figure out what our truth table is going to look like. And I'm just going to use the same as our AND truth table, but add in green what it's going to be. Okay, so given that we have a NOT gate here, all we have to do is invert our outputs here. So we would have a 0 for this because our output for the AND gate was 1, and the NAND gate is simply the opposite. So we would have 0, 1, 1, and 1. So now you essentially understand the basics of logic gates, and this is a very important concept to grasp because you are going to need it with whatever you do with electronics. So, please, give me any feedback if you can. I enjoy learning how to do this better, but let's stay tuned and we can learn next about Boolean algebra, which is essential in understanding computers. Thank you so much for watching.